All right, so we're on 3.1e, log and natural log function. This is our second to last section before this section. So tomorrow we do F, right? Yeah, after E is F. I knew that. We do 3.1 F, and then that's it for this unit. And then we will review on Wednesday, test on Thursday, okay? And that's it for this unit. And then we're in for the next unit, and the next unit is like one of our longest units. So yes.
We're not here tomorrow for the next day, whether we'll.
Yes, I mean, no choice, but yeah, of course. We will follow whatever happens, okay? But that is our projected plan of the week. Shh, does that make sense? So we have the projected plan of the week. Okay. All right, we're gonna start off with this. Here we go. So we've all gone through the ability to identify domain, range, intercepts. And guess what? It does not change just because the function changes. Does that make sense? The rules still are the same. Your domain is still asking you from left to right, what is happening, right? Your range is asking you from bottom to top, what is happening? Your intercept, where do you cross the X and Y axis at? Your asymptote, is there a boundary line that you see? And is the function increasing or decreasing? So as you read from left to right, what is the graph doing? Okay, those are things that we've been doing all year. Has not changed, still the same rule. The function just is different. Does that make sense? Okay, so this applies to all log functions, log base b of x. In order to graph, you have to have b has to have a value. So we're gonna let b equal x, that b equal 2, in order to have a graph. When b equals a value, what ends up happening is that 1, you're gonna always cross at 1, 0. Why do we always cross at 1, 0? Because it ties to our exponentials. But the reason why we cross at 1, 0 is because anything to the 0 power is 1, right? Anything to the 0 power is 1. And a log is asking this base to what power makes this value, right? And so anything to the 0 power is 1. So if I am at 2, log base 2, I'm saying 2 to what power is 1? 2 to what power is 1 is 0. Because anything to the 0 power is 1. So that's why in a parent function, you're going to always have 1, 0. Okay. After that, you're asking yourself. So notice our next point that we have here is at 2, 1. Do we see 2, 1? Okay. That's saying my base is 2. So 2 to the 1 power is what? 2, right? 2 to the 1 power is 2. This when you're at 1, that's telling you what your b is. So the value at 1 is telling you your b. Whatever the x is, that's your b. Then we keep going, and we're here at 4, 2. And it's asking you 2 to what power makes 4? And that would be 2, right? 2 to what power makes 4? 2. And then the next one that we have on here that we can see is 8, 3. So you're asking 2 to what power makes 8? And the answer would be 3, right? Because 2 cubed is 3. 2 cubed is 8, not 3. That's 2 times 2 times 2, okay? So these are our values on here. Now, as our b value changes, guess what's going to happen? All of these are going to change, right? Because now you're saying, if this is a 10, then you're saying, what to what power makes this? What to what power makes this? 10 to what power? 10 to what power? Okay. All right. So your domain. What is our domain? Where does our graph start? It starts at 0. So our domain is 0 to infinity, or we could say x is greater than 0. Agreed? Our range. What are our y values doing? What is our lowest y value? Exactly, they keep going. So what will be our lowest? Negative infinity. Our intercept, where do I cross the x and or y axis? At 1, 0. I have an x-intercept, but no y-intercept. And the reason why we don't have that y-intercept is that imaginary boundary line. And what is that called? An asymptote. We have an asymptote at 0. So even though it looks like I'm getting close to zero, am I actually ever touching zero?
No.
No, I'm not. I have a vertical asymptote at x equals 0. All right, and then is the graph increasing or decreasing? It is increasing. And when we describe increase, we describe from where does it start to where does it end? Well, we start increasing at 0 and we continue to forever. Okay, these are going to be the same properties for all of our log functions. Okay, these are going to be the same properties for all of our log functions, all of our parent functions of logs. The only thing that's changing is your base, right? So the only thing that's changing is the base, but the properties are going to stay the same. So for example, looking here at common log. Why is it common log? Because it says I'm going to let b equal 10. And when I let b equal 10, that's the common log of, that's just log x, right? And we call this our common log because it's the one that's most commonly used. And on your calculator, when you press the log button, that's the one that automatically gives your base a value of 10. Okay. Now,
What was the first?
it was just log of any base. But we let b equal 2 because you had to give b a value in order to graph. Okay. Now, looking at common log, notice here how we still have what? 1, 0. And that's still going to be any base to the 0 power is going to equal 1. But now we have, here is our 10, 1. Okay, and what do we say was significant when your y is 1? That means that the x is your b, right? Did anything else change? No, everything is still the same. Your domain is still 0 to infinity. Your range is still negative infinity to infinity. Your only intercept is still at 1, 0. Your imaginary boundary line, your asymptote, is still at x equals 0. And the graph is still doing what? Increasing. All that's going to change are the values after 1, 0. Technically, the values before 1, 0 are changing too, but they're so small that it's insignificant for us to even like identify or point out. Does that make sense? Mm-hmm. Okay, and we're still increasing from 0 to infinity. Okay, the shape of the graph is changing as far as it's stretching or compressing a little bit. But other than that, did anything else change? No, it did not. Okay. All right. So keeping that in mind, these are our parent function transformations. Okay. For log. Do they look different than anything else? Nope. Same thing. Same rules. Okay. Key thing to remember with your log, your b has to be positive and your b cannot equal 1. It has to be positive and it cannot equal 1. Huh? If you have 1 and then anything to the 1 power is just going to be 1. So, yeah, it's just, yeah. All right. Translation. So our first is our vertical translation. If I'm adding something to the log, that's my D. And if I add, that's going to cause me to go up. And if I subtract, that's going to cause me to go down, right? Same rules have already applied. C, I'm with the X. And key thing to remember, our X's are liars. Okay? So if it looks like I'm subtracting, I'm actually adding. And if it looks like I'm adding, I'm actually subtracting. So in order to shift to the right, it's going to look like subtraction. In order to shift to the left, it's going to look like addition. Notice how we use quotation marks now. All right. Last piece is our A. That's our stretch, compression, and reflection. Okay. A tells us a lot. The absolute value of A, so whether it's negative or positive is irrelevant, but if A is greater than 1, that's going to be a vertical stretch. If the absolute value is between 0 and 1, it's going to be a compression. And then if A is less than 0, meaning if A is negative. So if it's negative, that tells me that I am being reflected, right? Are these the same properties that apply to exponentials? Are these the same properties that apply to our quadratics? Yes, these properties are going to be the same all the way through. Got it? All right. So really quick, I would like for you at your tables to take a moment and to graph the two. And we're going to call this one y1 and call this one y2. So graph the two transformations. Well, tell me what they are and then graph them. Okay. And you're using your parent function log base 2. So the very first graph that we did. Got it? All right, let's give you some time. So on the first one, on your y1, what was the transformation?
Left 4.
Left 4, because your c equals -4. Even though it looks like a plus 4, it's minus -4, right? And it's your x is a liar. So that means that we're moving left 4, right? So I'm taking every value on this graph and shifting it left 4. Does that make sense? Okay. So that's the first thing I'm going to do is take every value on there and shift left 4. So I'm going to draw I probably should have drew this in a different color, but it's too late. It's happening. It's happening. Okay. Or how are you going to move to the left? All right. So my asymptote was here, but now it's also going to have to move to the 4th, right? 1, 2, 3, 4. So now here is my asymptote. I had 1, 0. And what's going to happen to that? So 1, 2, 3, 4. So it's now here. I was at 2, 1. And what's going to happen? 1, 2, 3, 4. It's at, do we see what's happening?
-4, -3, -3, 4.
-3, 4. The next one?
Yeah. No, like yes.
So I'm taking this point. I was here. 2, 1. 1, 2, 3, 4. I'm at -2, 1.
I'm talking about the 1 and 0 first point.
I was at -3, 0.
Okay.
Yeah. And then here, I'm moving this point and I'm moving this point.
So are we?
I'm not gonna move. We're not gonna move it upwards.
No, not on the first one. We're not there yet.
All right.
On our first transformation is to the left. Our second one is what causes us shift up and down.
So
Okay.
we're not writing so we're writing 2 different dots, like 2 different lines.
It's 2 different graphs.
Oh, I thought we were combining them together.
Nuh-uh. It says you have a y1 and a y2. It was y equals, unless it was written as one whole, it's 2 separate actions.
Yeah, so
Okay.
we're doing 2 different lines on.
Yes. So 1, 2, 3, 4. And so this is going to be at 0, 2. Do we see that? That's all I'm doing is shifting my parent function values and creating a graph. And that's good enough. I have 3 points. I can kind of make it do from here, right? All right. So that was y1. Then y2, that's a d value. My d equals 4. And what does d tell me to do?
Multiply by
To
4.
Go up or down. So we're going to go up 4 units, right? So I'm taking all the parent function units and I'm moving them up 4 units. So when I look at my parent function or think about it, that means that this guy here is going to go 1, 2, 3, 4. Does that make sense?
Yep.
So I'm at 1, 4. I'm here. I'm going up 1, 2, 3, 4. Yes, that's all you're doing.
We're not moving to the left. We're doing that.
Why would we be moving to the left here? This function doesn't tell me to move to the left.
Wait, so X's are liars.
You're graphing this and that. Huh?
X's are liars.
Yes, that's when it's being applied. This isn't, this 4 has no effect on this X. This 4 is changing my Y's. It's causing me to go up and down. Okay? Shh. Guys. All right, so now I'm just, from here, I'm going, I was at 1, 0. Now I'm going to go 1, 2, 3, 4. I'm now at 1, 4. I was at 2, 1. I'm going to go 1, 2, 3, 4. I was at 4, 2. Now I'm going to go 1, 2, 3, 4. And my asymptote didn't change, right? because I didn't go left or right, so therefore my asymptote is gonna stay where it's at. Pretend that I'm drawing the best curve you've ever seen and that my points are all beautiful, but that's what it would look like. So this is my transformations for y2. This is my transformation for y1. Okay, everything is based off of the parent function. What are you doing to that parent function? Am I shifting it left and right? Am I going up or down? Am I reflecting? Okay. At this point, we should be fairly comfortable moving parent functions around, guys. All right, remember in the beginning, we talked about making a table. If you still need to go back to making a table and adding and subtracting to your table, please, please, please do that. All right, next example. Now we're going backwards. So now we're given the graphs, and it says that the graphs are our, one is the parent function, and one is the transformation. So looking up here, which is our parent function? The red one. This is our PF, our parent function, right? So we know that red, in my case, is red. Yours, I know, is not in color. That's our parent function.
Wait, how do we do that again? If ours wasn't red, like.
Which one looks the most like your normal, your original? Unchanged,
Oh, okay, what if we like misguess it?
then you're wrong.
There's not anything other. we
Emma, are
can
you
tell?
really gonna look that the blue one is the parent function?
No, but I'm in a case where it looks like that, I might say it, but
I would say it.
I feel like I could, yeah, I could say that was a parent function. There's no other clues I could use that.
Aaron is negative.
Well, there are clues. Our parent function looks like this.
You know what it looks like.
Oh,
you know?
so we're using this. Okay.
Okay, so our parent function is the red. For most of us, we agreed, right? Because it's our parent function, we learned that to figure out our base value, we look for what? We look for our B. And so how do we know that this is our B?
Because it's at the one.
It's exactly, it's at the one with the Y. When Y equals 1, that tells us our B. So our parent function here is Y equals log base 3 of X. Because with the 1, what is our base? 3. Right? Make sense? Okay. All right. The blue is the transformation. So we're asking ourselves, how did the red become the blue?
Reflection.
It got negative.
There we go. Good job. It was a reflection. Perfect. And because it was reflected, how does that change our equation? So what changes in the reflection, what changes in the equation to make it a reflection?
The A is less than 0.
The A is less than 0, which means that it has to be a negative. So this is how we would represent that transformation. So the parent function we identified as the red, and that the base is 3. And then we realized the only thing that changed was it reflected over the x-axis. In order to reflect over the x-axis, our A has to be less than 0, which means it has to be negative. Okay. All right. Okay. All right. We went way past our time of getting to our thingy, by the way. Took a little bit longer than I thought on you guys doing the transformation practice, but here we go. We're just going to finish it out with the notes, and then we'll start our exit ticket as a morning. We'll figure it out. Here we go. Yes, it's 2 questions. It's 2 questions. Yes. The profits in dollars from subscriptions to a local newspaper are shown by the formula. P of X equals negative K plus 60 log base 10 of X, where X is the number of subscriptions sold and K is a constant. Find K if the newspaper makes a profit of $35 from selling 100 subscriptions. Okay. So the first thing you do with a word problem is read. Did we read? Yes.
No.
The second thing you do is mark the text. My pen did some weird things. Okay. We're going to mark the text. So marking the text means you're identifying key information. Well, the function is a huge key information. Okay. What X represents is key. X is your subscription. K is your constant. Circling what we're looking for. What are we looking for? K, and then our given information, right? Profit is 35. That's important. And our subscriptions are 100. Okay, there we go. Third thing is to identify your variables. So, like Z said, our X is what? 100. And our P is 35. So we identified our variables. The fourth thing is to plug in your variables. So we're going to plug in our variables. So we know P is what? 35 negative K plus 60 log base 10 of 100. Fifth is to solve. So we're going to solve. So we read, we marked the text, we identified our variables, we plugged in our variables, and now we're going to solve. What does it mean when you have log base 10 of 100? What is this asking us? There we go. The base to what power is the argument, right? So 10 to what power equals 100? 10 to what power is 2? So now we know that 35 equals negative K plus 60 times 2, because that's all this is asking. 10 to what power equals 100. Now that something was in algebra 2, now became a middle school math problem, right? Can you solve for K?
Yeah.
All right, solve for K. Finish her out. Got it.
You're welcome.
Yes. Ready, Brady? Finish it up. All right, what's our K? 85. Let's check it. Okay, so we should have had 35 equals negative K plus 120, right? Subtracted your 120. And 35 minus 120 gives us negative 85. If I have a negative on both sides, they cancel, they both become positive. So the answer is 85. All right. Yes. Remember, word problems look like they're the hardest, but they're actually the easiest usually mathematically. They just want to make sure you go through the steps to find the solution. Okay. All right. I know we don't have time to do the exit ticket, but I'm asking nicely. Can you please do the exit ticket and then we'll check it before we continue tomorrow? Okay. Huh? Oh, yes. If you finish, go ahead and turn it in.